Okay, so I got a number of questions about um, some specifics related to the homework assignment from last night. Um, I responded to those questions in mastering. Um, what I'll tell you, for those of you that are calling for more practice, just more time with the material, the good news is what we're talking about today is basically the same thing over again, with one extra step built in. So, I think one of the things that we ran into for those of you that did the assignment was the wording of some of the questions was different. And so it wasn't as apparent how to start. But once you figured out how to start, you generally did okay with it. Certainly, if you have more questions about those kinds of things, send them my way. And certainly don't be afraid to use the email or messenger or any of those kinds of functions to send me questions in the moment rather than at the end of the assignment, because I might not see them until Monday or something like that. Let's start off with a question here, though. We're getting into a concept known as limiting reactants, and I want to ask you this question. We're focusing on the concept overall about completion. Do all reactions go to completion? And the answer to that question is yes. All reactions do end up completed, at least to an extent that they're able based upon what is there. But that doesn't necessarily mean that all of the things that I start with will ultimately react. So let's take this example here. Carbon is reacting with oxygen to make carbon dioxide. That is the reaction that takes place when we burn charcoal. So set up a barbecue grill outside, you put the charcoal in, you ignite it. This is the reaction that's taking place. Carbon in the charcoal is reacting with oxygen in the air to make carbon dioxide. My question to you is this. This is what I want you to answer. If we were to take one of those charcoal bricks and light it, and then put that lit charcoal brick into a glass jar and close it up, what would happen? What would run out first? So that's what I want you to put in to Pear Deck right now. I think we all know the answer of what will happen. The flame is going to go out at some point. My question to you is why? What's going to run out first? Am I going to run out of charcoal, or am I going to run out of oxygen inside of that jar? All right, if this is your answer that depends on how big and how big, I like what you're thinking. You are correct. But let's make some assumptions here. Let's say that we're talking about just a standard size glass jar and a lump of charcoal like what you would get in a bag of charcoal for your grill. Let's work on those assumptions. Absolutely right, though. It does. There is a factor of size and quantity there that we're going to get into. And we're all on the right track here. So experientially, we know that the charcoal's probably going to have some leftovers after that flame goes out. What we're describing in that scenario is something called a limiting reactant. A chemical reaction is limited based upon the quantity of the reactants. So I can't have a chemical reaction go on forever in infinity. At some point, the chemical reaction is going to stop. And it's going to stop because at some point, we're going to run out of one or more of the reactants. Well, we've got names for those. The reactants that run out, those are our limiting reactants. If there are any reactants that we have leftovers of, like the charcoal in that particular example, we call those excess reactants. The third term there is kind of what we would consider a perfect storm. The stoichiometric amount would be, well, what if I have exactly the right amount of charcoal and exactly the right amount of oxygen so that they completely react with each other and there's no leftovers? The reason it's called the stoichiometric amount is because the only way that we would actually get that value is we'd have to calculate from stoichiometry how much of each to measure. So these are the terms that we are working with today. Limiting reactant, excess reactant, and to a lesser extent, stoichiometric amount. We're going to introduce a fourth term here a little bit later when we start talking about the product of these reactions, but we'll cross that when we come to it. Any questions about these three terms? All right, so before we get into some chemistry, I want us to look at this concept of limiting reactants from another standpoint. Now, again, in your textbook, they focused on pancakes. I'm going to give us a slightly different example here just so that you have some variety. Let's say we're in this scenario. We're selling cheeseburgers for a fundraiser. Rather than cooking them to order, which anyone who's ever worked in a fast food restaurant knows, cooking to order stinks. I worked at Wendy's for 2 years to put myself for the first 2 years of college. I worked that grill. It was horrifying how many burns I got on my hands over the course of a 9-hour shift. And that's exactly what it's supposed to be cooked to order. Cooking to order stinks. So we're going to save ourselves some time. We're going to pre-make everything. Here's what our cheeseburger looks like. We're going to make them uniformly so that it's easy to pack, it's easy to serve, it's easy to sell. Each cheeseburger is going to have a bun. It's going to have a patty. It's going to have a slice of cheese. It's going to have 2 slices of pickle, 3 slices of onion. That's our cheeseburger. Okay, we're getting to the end of the day. We're about to pack up our last things. Here's our question. If this is what I have left, how many cheeseburgers can we make before we call it a day? If you haven't responded yet, throw out your best guess. Remember, we're not evaluating correctness here. We're going to tell you the correct answer anyway at some point. Based on what you're thinking, based on what you know, put out your best guess here. Okay. So we've got a lot of different responses. Let's think this through. The easiest way to solve a question like this is to simply just figure out how many burgers each one of those ingredients could make. So for example, my 13 buns, well, that would make 13 burgers. My 5 pounds of meat, well, a quarter pound is needed for each patty. So that means I can get 4 patties out of every pound. 4 times 5 would be 20. My 25 slices of cheese would make 25. My 100 pickles would make 50. My 30 onions would make 10. Okay, so the correct answer here is 10. As soon as I run out of onions, I'm no longer going to have a cheeseburger, at least according to the recipe that we set out for cheeseburgers. Now, could you make an argument that you still have a cheeseburger if it doesn't have onions? Yes, technically, but that's not the point of this particular exercise. The point of this exercise is that is the exact recipe, and after the 10th burger, we can no longer follow that recipe. So under this arrangement, we can make 10 cheeseburgers. Using our terms, the onions would be our limiting reactants. They are going to be the thing that runs out first. They're also going to be the thing that dictates how much product, how many cheeseburgers we're able to make. Everything else had leftovers, right? We had extra pickles left over. We had extra meat left over. We had extra buns left over. We had extra cheese left over. We would qualify all of those as being excess reactants. Now, what if we were actually doing this using a chemistry problem? Well, the good news is, from a standpoint of process, the process is identical to what we did on Wednesday. The only difference is that we're going to have multiple things to do calculations with. And we're going to have to apply this same kind of principle that we did with the cheeseburgers. In the cheeseburger example, the easiest way to solve that problem was to take each one of those ingredients and figure out how many burgers it made. And then choose the one that made the fewest burgers. In a chemical example, it's the same thing. I take this reactant, and I figure out how much product it's going to make. I take this other reactant, and I figure out how much product it's going to make. The one that makes the lesser amount of product, that's my limiting reactant. The amount of product that is made, we've got a term for that. We call that the yield. More precisely, we call that the theoretical yield, because it represents the amount that can be made in the most ideal of circumstances where every single bit of reactant turns into product. And there are no side reactions, there are no unreacted pieces of our reactants or anything like that. We don't get a whole bunch of it that's lost to the solution or anything like that. So let's take a look at a couple of examples of some limiting reactant problems that you might see in the homework over the weekend or on next week's quiz. And we'll take it from there. So here we have a reaction between acetylene and oxygen. Acetylene reacts with oxygen to make carbon dioxide and water. The question that we have here is, what reactant is the limiting reactant? Now, for questions like this, where we are not concerned at all with yield, there are two ways to approach. One way to approach this problem is to take one of those reactants and turn it into the other reactant and compare it. This is probably the easiest approach for determining the limiting reactant because it means that we only have to do one calculation. So let's take the 52 grams. So 52.0 grams of acetylene. And we want to turn it into grams of oxygen. So just like we mapped out on Wednesday, we're going to need 3 conversions to do it. We're going to turn the grams of acetylene into moles. We're going to turn the moles of acetylene into moles of oxygen. And then finally, we're going to turn the moles of oxygen into grams. So starting with our 52 grams of acetylene, the first step is to turn the grams of acetylene into moles. For that, we need our molar mass. Molar mass comes from the periodic table. So we've got 2 carbons, so 2 times 12.01, and 2 hydrogens, 2 times 1.01. Total mass of acetylene is 26.04. My grams of acetylene cancel. Now I've got my moles. The second step is to turn the moles of acetylene into moles of oxygen. For that, I need my balanced chemical equation. So I need the coefficients in particular, 5 from the oxygen, 2 from the acetylene. My moles of acetylene cancel. Now I have moles of oxygen. Final step, I need to turn moles of oxygen into grams of oxygen. For that, I need a molar mass. Molar masses come off of the periodic table. Molar mass of oxygen is 16. 16 times 2 is 32. So my moles of oxygen cancel. Now I've got grams of oxygen. Now I just need to do the calculation. 52 times 5 times 32 divided by 26.04, divided by 2, to 3 significant figures, because I only have 3 here from the start. 160 grams of oxygen. Now, the tricky part here is in the interpretation. I just converted the 52 grams of acetylene into 160 grams of oxygen. What that tells me is this is the amount of oxygen that I need to run the reaction. The question is, do I have 160 grams of oxygen? I have that and then some. So what does that tell us about the oxygen? Do I have enough oxygen here? Yes. Do I have more than enough oxygen here? If I have more than what is required, that means that I've got the excess reactant in the oxygen. This reaction takes place, there are still 28 grams of oxygen that have not done anything. So we compare the 188 grams that we started with is more than the 160 that we needed. So oxygen is excess. If oxygen is excess, that means that the acetylene, the C2H2, is the limiting reactant. LR and XS are common abbreviations that we can use to mark the limiting reactant, LR, and the excess reagent, XS. Could you work this the other way? Yes. So if you started with 188 grams of oxygen and ran the conversion the other direction, what you would have found is that the amount of acetylene required would be more than what you have. And so the interpretation would go the other way. The starting amount is less than what is needed, so that must be the limiting reactant that we're looking at. All right, questions with this. So this is the specifics for if I'm just looking for the limiting reactant, this is what I can do. If I'm asked to figure out the yield, then I need to do a little bit more. So take this for example. I've got nickel 4 sulfide reacting with oxygen to make nickel 2 oxide and sulfur dioxide. We've got 11.2 grams of nickel 4 sulfide, or excuse me, nickel 1 sulfide. Wait, which one is it? It's got to be the nickel 4. Oh, sorry, I didn't catch that before. So I'm looking at NiS2. So I've got 11.2 grams of that and 5.34 grams of oxygen. The question is, what is the limiting reactant and what is the sulfur dioxide? So I need to know the limiting reactant. I also need to know the theoretical yield. When we have problems like this to answer, This is when we want to go back to that cheeseburger kind of way of doing things. Take each one of these and convert it into sulfur dioxide and see which one makes less. That'll tell you simultaneously which one's the limiting reactant and what the yield is. So we've got two different calculations that we're going to do here. In the first calculation, we're going to turn the 11.2 grams of nickel sulfide into sulfur dioxide. So I need to turn it into moles. And then in a completely separate calculation, I need to take the 5.34 grams of oxygen and do the same calculation. Turn it into moles, turn the moles into grams. So let's start with the nickel, since it was first. 11.2 grams of nickel 4 sulfide. My first step is to turn the grams into moles. For that, I need molar mass. Molar mass comes from the periodic table. Nickel is 58.69. Each sulfur is 32.07, and there are two of them. Total mass is 122.83. My grams of nickel sulfide cancel. My next step is to turn the moles of nickel sulfide into moles of sulfur dioxide. For that, I need the balanced chemical equation and the coefficients from it. So 4 from the sulfur dioxide, 2 from the nickel sulfide. My nickel sulfides cancel. Last step, I need to turn the moles of sulfur dioxide into grams. For that, I'm going to need a molar mass. Molar masses come from the periodic table. Sulfur, 32.07. Oxygen, 16 each, and there are two of them. 64.07 is the mass there. My moles cancel. I'm left with just grams. Now I do the calculation. 11.2 multiplied by 4 multiplied by 64.07 divided by 122.83 divided by 2. For 3 significant figures, I get 11.7 grams of sulfur dioxide. Do I know if that is correct or not? I know the calculation is correct, but is it the actual answer to the question? I don't know that yet. And the reason I don't know that yet is because I haven't figured out how much the oxygen would make. So I've got to do that calculation as well. So we're going to do the same essential calculation, 5.34 grams of oxygen. My first step is to turn the grams of oxygen into moles. For that, I need the molar mass. Molar mass comes from the periodic table. 16 times 2 is 32. Grams of oxygen cancel out. My next step, I want to turn the moles of oxygen into moles of sulfur dioxide. For that, I need the balanced chemical equation. I need the coefficients from it. 4 from the sulfur dioxide, 5 from the oxygen. My moles of oxygen cancel. Oops. Ahead of myself. My last step, I need to turn the moles of sulfur dioxide into grams. Now, ordinarily, we would need to go to the periodic table for this. However, when we do these kinds of calculations, what we should realize is that the last step of them is the same. Because I have to convert to the same product. So I've actually already calculated that molar mass. I did it up here. So I can save myself from going back to the periodic table and recalculating it again. So now I just need to do the calculation itself. 5.34 multiplied by 4 multiplied by 64.07 divided by 32 divided by 5. The three significant figures, 8.55 grams of sulfur dioxide. Okay, we've done both sets of calculations now. Now we've got to figure out what it means. Go back to the cheeseburger example. Which one's running out first? The oxygen. It's making less product, so it must be running out more quickly. So what's my limiting reactant? Oxygen. What is my theoretical yield for sulfur dioxide? It's the calculation I did with oxygen, 8.55 grams. So this is a really common limiting reactant kind of problem, where it just gives you an equation, it gives you a couple of reactants, and it says, figure all this out. Good thing is, calculations mirror each other, and we usually solve both questions at the same time. The best way to find the limiting reactant in a problem like this, where we also have to find the yield, is to calculate the yield for both reactants and figure out which one makes less. Just like we did in the cheeseburger problem. I'm gonna skip this problem here because we don't have enough time to do it. I want to give you more than 4 minutes to actually complete it. So instead, what I'd like you to do, or what I'd like us to do, is let's take a little peek ahead to Monday. On Monday, we're going to take the concept of yield and start to expand it. So we already talked about the idea of a theoretical yield. That is the yield that we would expect based upon the calculations that we're doing for the limiting reactant stuff. That tells us, okay, if I do this reaction as it is written and everything goes right, this is how much product I should expect. That's why it's called theoretical yield. Theoretically, I should get every molecule out that I was supposed to. In practice, that rarely happens. We run into issues of purity, we run into issues of side reactions, we run into issues of completion. So the actual yield, the yield that we get when we do the experiment is usually different. One way that we can calculate the efficiency of our chemical reaction is through something called percent yield. Now, for those of you that are interested in maybe looking into a career in engineering, the concept of efficiency is very closely related to this concept of yield. Usually when efficiency is described, it's basically this part of the equation without the times 100%. But we can look at calculating yields and calculating percent yields through this pretty simple equation. If I take what was actually done versus what we should have gotten and multiply that ratio by 100%, I get percent yield. Right, so as you're doing this last question for the day, let me give you some insight for next week. So on Monday, we are going to do some more questions. We're going to do a couple of calculations related to limiting reactants and percent yield, give you some opportunities to practice both of those things. The majority of the quiz next week is going to be over those kinds of calculations. And then what we're also going to do is next week, we're going to be looking at chapters 9 and 10 together. Now, I want you to take that with a slight grain of salt because we're not going to be going through the full chapter 9 or the full chapter 10. We're going to be kind of hitting on highlights from all of them that are all related together to talking about electrons and talking about bonding. And that's about the extent of what we're going to do out of those two chapters. So just be aware, be on the lookout. I will be sending you the PowerPoint for that combined chapter 9 and 10. It'll be in Blackboard this weekend. But Monday, we're going to finish this off and get things kind of rolling through chapter 9. And then the rest of the week will be with chapters 9 and 10 as well. Have a great weekend.